Hi, welcome to Dissolved Chemistry. Let us continue our discussion on this equilibrium. In the previous video, we initiated our discussion on this ionic equilibrium, where we have discussed various aspects like electrolytes and non-electrolytes, and then classification of electrolytes into strong electrolytes and weak electrolytes. And then we have seen these weak electrolytes are undergoing partial dissociation upon dissolution in water. And as they are undergoing partial dissociation, then there is a dynamic equilibrium is being established between ionized and unionized form. And that dynamic equilibrium, we defined it as what? Ionic equilibrium. Okay. In the present video, we will discuss regarding acids, bases and salts. Well, these acids, bases and salts are the compounds which occur in nature, okay, in widespread, okay. For example, if you take hydrochloric acid, one of the major component of gastric juices which are secreted by the special lining of stomach in our body, and almost 1.2 to 1.5 liters of this acid is secreted per day. Okay, and which is helpful in digestion of particularly carbohydrates. Okay, similarly, if you consider, okay, first one is hydrochloric acid, one of the major component of gastric juice. Okay, and then you can take acetic acid. Okay, it is one of the major component of vinegar. Okay, so which occurs naturally. And apart from this, you can take citric acid, okay, ascorbic acid as the major component of citrus fruits, okay, like orange, or you can take lemon, we call citrus fruits. Fine, then later you can take your tartaric acid. Okay, it is the major component of your tamarind paste. Okay, so these are all the examples of how these acids are going to occur naturally. When we look into its taste, usually these acids are having sour in taste. Okay, and when you go with litmus test, then it turns blue litmus to, these compounds are going to turn blue litmus to red. Okay, and another important property of these acids is that they liberate hydrogen gas upon reacting with metals. Yeah. So this is another property of what? Acid we can call. Similarly, bases are the compounds which turn what? Red litmus to blue. Blue litmus, and generally they are bitter in taste and soapy in touch. Okay, when we touch, it will be having smooth soapy touch, we call that one, right? And important example is your washing soda. Okay, many are there, just one example I am quoting here. We will take different examples later. Washing soda, and they have a property of cleansing, and they are being used as washing soda, and it is nothing but your sodium carbonate, Na2CO3. Okay, so that is bases. When in proper proportion, acid and base, if we combine, acid and base, if they are combined, generally they will give salts, or the compounds resulting will be called salts, plus water we will get. Okay, important example we will take. For example, HCl, hydrochloric acid, base you can take NaOH, and you will be getting what? NaCl plus water. Okay, so this NaCl is called salt. Similarly, many salts are formed by the combination of acids and bases. Fine. So these compounds, generally salts, if you take, all are ionic compounds. Generally they are crystalline solids. Okay. And these solids are formed by the aggregation of cations and anions. Okay. By electrostatic force of attraction. Okay. So that is how these salts are being formed. Okay. Generally remember, acid base, when they combine, when they react, generally they form water plus salt. Okay. And they are readily soluble in water, most of the salts. Right. Fine. We will move on to various theories which are being proposed to explain or to define the acids and bases. Okay. Theory of acids and bases. Okay. So according to this theory, any compound which upon dissolution in water, if it dissociate and furnishes H plus ions or gives H plus ions, then those compounds are referred as acids according to this definition. See here, I will illustrate. Say you take water. In that water, if you add any compound, okay, still we will not call it as acid. If we dissolve this compound in water, then if it forms H plus ions, if it dissociate to give H plus ions, then that compound is called acid. Okay, for example, now take the example that compound is HCl. Now if you bring this HCl in contact with water, or if you dissolve it, so then what you will be getting? H plus aqueous, Cl minus aqueous. Okay, so here we will write HCl plus H2O. Okay, we will write H plus aqueous plus Cl minus aqueous. So as it is donating this H plus, we call this HCl as what? Acid according to Arrhenius theory. And we should remember that this H plus is a very small, tiny and highly reactive what? Ion. So therefore it won't exist as H plus in water. You should remember that it is being accepted by water molecule, non-bonding pair of water molecule. So it will combine and form H3O plus. Okay. To represent this H plus, usually we will refer this as H3O plus because it is occurring in the form of H3O plus in water. Similarly, what is base according to Arrhenius theory is any compound which upon dissolution in water gives OH minus ions, which furnishes hydroxyl ions. See, compound upon dissolution in water, if it furnishes OH minus ions, aqueous, then those compounds are referred as what? Bases. Okay. So important and simple example, we will take sodium hydroxide, which upon dissolution in water, it will give Na plus aqueous plus OH minus aqueous. So therefore, NaOH is called base as it furnishes hydroxyl ions. Okay. So this is what is the acid base concept of or theory of Arrhenius. Okay. Now this definition or this theory has limitations, that it includes only those compounds which can donate H plus and only compounds which can give OH minus upon dissolution in water. There are many other compounds such as ammonia, okay, so which can also act as what? Base, right? So, but it is not included in this definition. So, therefore, include more compounds in the definition of acids and bases. Another theory was being proposed, okay, which is more inclusive one, and that we will see. And that theory we call it as what? Bronsted and Lowry concept of acid and bases. Bronsted, Lowry concept of acids and bases. Okay, it is also called as proton donor acceptor theory. NH3 we will take first. Okay, it is ammonia. So it is a base because it will accept the proton. Proton acceptor is called base. Proton donor is called acid. Base and proton donor is called acid. Now, according to the definition of Bronsted and Lowry, what we find, ammonia is a base because it is accepting the proton. Okay, proton acceptor we called as base. And here water is acting as what? Acid, which we call it as what? Proton donor. Here what? So ammonia is base, water is acid. Right? Now what happens? These are going to combine reversibly and there is an equilibrium is being established between the combination of ammonia and water to form ammonium cation and hydroxyl ion. So now when you look into this hydroxyl ion, okay, so it has one extra proton, okay, and it can donate back that proton to the OH minus. So therefore it can donate back the OH minus means what it is going to act as? Proton donating. So therefore it can act as what? Acid. This acid originated from what? By the accepting of proton. Okay, it was a base earlier and by accepting the proton it has formed. So therefore it is called as what? Conjugate acid. Conjugate acid of ammonia we call. And here this OH minus now have the tendency to accept the proton. Okay, so therefore this OH minus we call it as what? Conjugate base of water. Okay, and now this NH3 and NH4 plus are called conjugate base acid pair. Base and acid pairs. Okay. Similarly, water and OH minus are referred as conjugate acid base pair. Now what they differ, these conjugate acid base pairs? They differ in one proton, okay. One which is less with one H plus is referred as base. One which is greater with one H plus we call it as what? Conjugate acid. Okay, same thing we will see here. We'll take another one example and try to understand that one. Now you take HCl upon dissolution in water. It will act as what? Proton donor. Okay, HCl will donate the proton and form, we will be getting like this, Cl minus aqueous plus H3O plus aqueous. Okay, when you carefully look into this, now this here water is acting as a base. It is accepting the proton. See here H3O plus, accepting the proton and forming the what? Conjugate acid. What we call this as? Conjugate acid. Here it is base and it is forming conjugate acid. And similarly HCl is acid and it is forming what? Cl minus after donation of the proton. So therefore here it is acid and Cl minus is your conjugate base. And one thing you should remember, so conjugate base, if it is stable, okay, in aqueous medium, then we call it as what? Your acid is stronger. If it is what? Unstable, right? Then what we call it as what? Your acid will be weak acid, isn't it? Okay. Similarly, as we have seen this conjugate acid base pair, We will take another one example. Okay, try to understand this one. Now, for example, if you take CH3COOH plus water, okay, it will dissociate to give CH3COO minus aqueous plus H3O plus. Okay, here water is acting as base and acetic acid is acting as what? Acid. It is a proton donor, so therefore it is acid. It is a proton acceptor, so therefore it is a base, and it forms acetate ion is conjugate base. Okay, and here H3O plus is conjugate acid. Now, as this conjugate base is unstable, okay, its stability in water is very less, so therefore generally it will take back the proton from the H3O plus to form acetic acid. Therefore the equilibrium is maximum shifted in this direction. Okay, only less than 5%, okay, less than 5% is dissociated and greater than 95% is in the form of what? Acetic acid. What is the reason for that? Its conjugate base, that is acetate ion, is least stable. Okay, so therefore it is a weak acid. If it is more stable, as you see in the case of HCl, Cl minus, which is a conjugate base of acid HCl, so therefore it is highly stable in water, so therefore it will not recombine or reaccept the proton from H3O plus to form HCl, hence it is a strong acid and your equilibrium will be shifted in the forward direction. Okay, maximum it is in the forward direction, right? So that is what we call it as what? Conjugate acid base pair. And ammonia, its conjugate acid is highly unstable, it will give back the proton, so therefore maximum you will be finding in the form of ammonia, means it is a weak base we call. If the conjugate acid or conjugate base are stable in water, then the given acid or base will be stronger we call. If it is highly unstable, so then we call it as what? Your acid or base will be weak. Okay, so that is how Bronsted and Lowry theory is being explained. Okay, the next important aspect is which is still more broader definition is being given, that we call it as what? Levy's concept of acids and bases. Okay, so let us see that one. Electron pair donor acceptor theory. Okay, according to this, any compound which donates electron pair, we call it as what? A base. Levy's base we call. And any compound which accepts electron pair, we call it as what? Acid. Levy's acid. Generally, Levy's acids are electron deficient species. Deficient species. Okay, and Levy's bases are electron rich species. Hence they donate and act as what? Levy's base. Donate, and these are going to accept the electron pair. Okay, important example we will take electron deficient species like boron trifluoride, which is having one vacant orbital on the central boron atom. We know that one. Okay, hence it is always having electron affinity. So therefore NH3, as it is got with one non-bonding pair available, so therefore it will act as a donor. Electron pair donor means base, and your boron trifluoride acts as acid. So therefore it will donate the electron and form the bond. Boron trifluoride NH3 bond is going to form. Okay, so this is how we are going to. It is electron pair acceptor. Okay, electron pair acceptor. And this is electron pair donor. Okay, so this is how we are going to define Levy's acids and base. Okay, other examples are for Levy's acids. Lewis acids. Examples, other examples are, you can take AlCl3, you can take your magnesium +2, you can take your cobalt +2. It can also act as Lewis acid. Okay, any electron deficient species which is in need of electron pair, we call it as what? Lewis acid. Similarly, Lewis bases are those compounds you can include. Okay, you can take your water molecule, okay, and you can take your ammonia, you can take your OH minus. So these are all are called as what? Lewis bases, because they got with electron pair and they can readily donate. Okay, hence they are called as what? Lewis bases. Now another important thing is, in both Arrhenius theory and in this Bronsted and Lowry theory, we have seen that this water, when it comes in contact with bases such as NaOH, our water is acting as what? Right? Acting as acid, and it is a base. Okay. So therefore, what you will be getting, Na plus aqueous plus OH minus aqueous. Right? Okay. And the same when you add with HCl, then your water is going to act as what? Base, by accepting the proton. Okay. Plus what you will, Cl minus aqueous. As it is acting as both acid as well as base, the water is called amphoteric. Okay. Water is referred as what? Amphoteric in nature. Okay. Water is called amphoteric. Fine. I hope you have understood the meaning of acids, bases and salts, and various concepts, that is Arrhenius concept, Bronsted and Lowry concept, and Lewis concept of acids and bases. Okay. The next video will continue with this ionic equilibrium. Thank you for watching. And please don't forget to subscribe our channel.